Hello, my name is Michael, and thermal acoustics or thermoacoustics refers to the relationship between heat and acoustic resonance. If you've ever needed to add air to your tires on a winter day, or maybe even blown up a sealed can of soup on a stove, you have observed thermal expansion. A loudspeaker produces sounds or acoustic waves by using mechanical movement to vary the air pressure. The air molecules, you can see, are more dense where there are peaks in the acoustic wave down below. We can illustrate the thermal acoustic effect by replacing that speaker with a resistive heating element similar to what's in your toaster. By turning the heating element on and off, we can vary the pressure in the air, similar to how the speaker does. The gas expands with the periodic application of heat. Recently, an alternative explanation was made, not based on thermal expansion. Instead, it states that the atoms of the thermally excited heat source exchange momentum with the nearby gas molecules, causing them to be rapidly ejected away. One of the earliest explorations of this effect was the 1917 thermophone by Arnold and Crandall. They used a very thin platinum film connected to a pure AC current source and successfully converted heat into sound. It is important to note that this system has no moving parts. Other successful attempts to utilize this effect have been made, and one especially notable one is the thermal acoustic engine, which uses heat to convert sound into mechanical motion. There are loads of great YouTube videos out there covering thermal acoustic engines, but there are surprisingly few on what I'd like to talk about. Both of the previous examples are actuators, the thermophone and the thermal acoustic engine. But a gas sensor can actually be constructed using the same thermal acoustic effect. Acoustic gas sensors use a microphone to monitor the amplitude of the induced acoustic wave. Thermal effusivity is a measure of the rate at which a material, be it gas or otherwise, absorbs or releases thermal energy, i.e., how long does it take our hot plate to heat all the way up and then cool all the way back down. Acoustic signal from the microphone is used to monitor the amplitude of the induced acoustic wave. The left graph shows this. The right graph shows the temperature of the heat source with respect to time. Ideally, the depth of this signal should be very large, with a very big difference in the minimum and maximum temperatures. This is achieved through high effusivity. We need both high heat and sufficient cooling, as the depth of this temperature difference influences the strength of our acoustic signal. Gases also have measures of effusivity. For example, the effusivity of CO2 is lower than that of zero air, which is zero grade air. Zero air is air that has been purified to remove the hydrocarbons. By monitoring the amplitude of our acoustic signal with the sensor, we can estimate the percent concentration of CO2 in an atmosphere of air. As the concentration of CO2 increases, the amplitude of our acoustic signal will decrease. Thermal acoustic gas sensors can detect different gases based on their unique effusivity by monitoring the amplitude of a thermally induced acoustic wave. The signal-to-noise ratio of this is controlled by the effusivity of the heat source, but can be improved using a second acoustically isolated microphone and post-processing. The transduction path is heat to sound to voltage, which gives you an estimate of percent atmosphere. While not yet widely adopted, these sensors might become more important. Recent studies have made strides in their CMOS manufacturability, and climate monitoring is becoming significantly more necessary. Thank you for listening. Further resources are available in the description.